To get the razor-sharp aesthetic of high-end fine dining, kitchens historically generate an astronomical amount of physical waste. Perfect cubes and precise spheres leave behind mounds of oddly shaped offcuts, skins, and stems. This puts modern chefs in a difficult position. They need dramatic, towering architectural garnishes to build verticality on the plate and justify luxury pricing, but they are increasingly bound by strict zero-waste sustainability mandates. The solution to this tension requires a shift in perspective. Instead of treating those discarded peels and bones as garbage, kitchens are treating them as vessels. They are raw materials holding hidden natural polymers. By breaking down these scrap materials and applying precise chemistry, chefs can reassemble them into sheets of fully edible, transparent structural glass. Culinary innovation now means engineering premium aesthetics out of the refuse bin, finding a way to turn a handful of zero-cost scraps into the most striking visual element on the table. The process starts at the cutting board. An apple peel destined for the compost is instead gathered up and dropped into a pot of boiling water to simmer. But we are not cooking to build a flavor profile here. This simmering phase is strictly an exercise in chemical extraction. We are doing material science. This diagram illustrates exactly what we are pulling out. We are isolating specific foundational polymers, pectin from fruit peels, heavy starches from potato skins, or structural collagen from discarded fish bones. After heavily reducing the water, we are left with a deeply concentrated liquid base. It holds all the necessary building blocks we just stripped from the scraps, but it completely lacks physical strength. Isolating these base polymers is the necessary first step. It breaks the food waste out of its original physical state, turning it into a concentrated fluid ready for modification. To bridge the gap between that fluid base and a solid structure, chefs turn to a specific chemical toolkit known as hydrocolloids. These are specialized ingredients that bind water to change its texture. Whisking in agar locks the fluid into a rigid microscopic lattice. Folding in glucose or isomalt fills the microscopic gaps, creating a glass-like, highly reflective finish. Finally, adding glycerol transforms the rigid joints into flexible nodes, so the final sheet won't shatter. With the base fortified, the liquid is poured flat over perfectly smooth silicone mats or acetate sheets to set. The thickness of this pour dictates the final texture. A shallow cast of just 0.3 to 0.5 millimeters yields a highly delicate, fully transparent crisp. Pushing the pour depth slightly higher to around 1 millimeter creates a much thicker structure strong enough to stand upright as an architectural sail on a plate. Next comes dehydration, which operates on a razor-thin margin of error. The sheets must dry under a constant temperature of 50 to 60 degrees Celsius, with high airflow to wick away moisture. If the temperature climbs too high, the process fails entirely. The sugars undergo rapid caramelization, the delicate colors darken, and the material loses its transparency. It is this precise mathematical manipulation of hydrocolloids and thermal physics that elevates an unstable organic liquid into a predictable, engineered architectural material. Out of the dehydrator emerge fully rigid, transparent sheets. They carry distinct colors and flavors directly inherited from their origin scrap, like glowing amber glass from apples or deep ruby shards from beetroot peels. While the material is still warm from the dehydrator, it remains pliable. Chefs can carefully bend these translucent orange carrot sheets over metal rolling pins or rings, setting them into permanent curves as they cool. These shapes lock into specific culinary roles. Aromatic citrus glass brings an acidic crunch to seafood dishes. Savory mushroom glass builds umami on roasted meats. Sweet, delicate pear glass forms elegant domes over intricate desserts. And the zero-waste cycle does not end with the extraction liquid. The fibrous pulp left over from that very first simmer is dehydrated and ground down into concentrated vegetable or fruit powders for seasoning. The absolute end of the line only occurs when the remaining fibers are completely exhausted of their culinary value. Only then are they finally composted rather than trashed. Engineering a discarded byproduct into the structural centerpiece of a dish changes how a kitchen values its inventory. It suggests that high-end presentation can be built from technical skill rather than just the price of the raw materials.